Welcome. My name is Jean, USound Product Manager at SELTECH, and I'm very happy to see you all joining us today. Let's start our webinar. What's your plan for today, Julio?
Yes, so thanks, Jean. Hi, everyone. Today we will have our partners from USound. Low distortion at high SPL is the main request acoustical engineers have on every audio product. This is especially true for miniature speakers where the size is limited. USound MEMS speakers are not immune to this area of conflict. This webinar will describe the Active Linearization Algorithm, also called ALA, a signal processing method of improving USound MEMS speaker linearity to reduce the overall THD significantly. We'll now leave Paris and go to Austria, where USound is based. So take a nice cup of coffee, relax, not too much, and enjoy this webinar and stay safe. Hi, Konstantin. Thanks for taking the time to share your knowledge with us. The platform is yours. Bye.
Bonjour, Julio. Bonjour, Jin. Welcome, everybody. Nice to see you. So today we will be talking about nonlinearities in microspeakers and how to compensate for them using an active algorithm. So using MEMS technology that we developed at USound, we have been able to develop loudspeakers that are much smaller than conventional electrodynamic loudspeakers, while still performing at the same or comparable sound pressure levels. However, the problems with miniaturization occur just as much with MEMS speakers as they do with electrodynamic speakers, namely the nonlinearities of the movement are a factor that cannot be completely ignored. Of course, the ideal microspeaker would have high SPL output with entirely linear behavior and zero nonlinear distortion. But as we all know, this is a utopian dream that cannot easily come true. So especially with microspeakers, this is the main problem that we have in application. We want to achieve a high sound pressure level while keeping the distortion below, at least below an audibility threshold. And how we can achieve that, other than, of course, tuning the loudspeaker to have as high a linearity as possible, is something that we will dive into today. So the way we describe nonlinearities is by looking at the characteristic curve of a loudspeaker. The characteristic curve is a measurement that shows, basically it shows the output of a device compared to its input. So if I input X amount of, in this case, volt, it should output X or Y amount of acoustic output or sound pressure. And ideally, this relationship would be completely linear. So if you increase the input level by a factor of 2, then the output, the sound pressure, should also increase by a factor of 2 or 6 decibel. Now, this is easily possible for small excursion levels, but the higher the acoustic output will be, the more the diaphragm and the systems have to move, the more nonlinearity you will introduce just by nonlinear components inside the system, inside the stiffness and all the factors that describe the system. The way we describe this is with the characteristic curve that shows us exactly the relation of the output level depending on the input level. And if we see that the characteristic curve deviates from a completely linear behavior, which in this graph would be just a straight line from -1 to 1 1. And we see a deviation from that linearity, then we see the mechanism that causes the nonlinear distortion. So in this graph, we see an example for a characteristic curve for a speaker with a significant amount of distortion. This would be the blue graph. And the idea that we're proposing here is that by compensating for that nonlinearity, by adding a transfer function that would be the direct inverse of the characteristic curve, which in this case is shown as the orange or yellow curve, then we can achieve in the end a transfer function that would be almost or completely linear, which we see as the combination of two curves, which would be the green curve in this case. Now, we do this with a digital open loop algorithm that we developed in-house that is capable of reducing the THD by actively compensating for those nonlinearities. But in order for this to work, of course, the nonlinearities of the loudspeaker must be extremely well known. So we need to characterize the loudspeaker. We need to measure it very accurately to get a feel of how the nonlinearities look like. So how the characteristic curve looks like over the full excursion levels. And the second problem is, if we want to apply this to a single speaker, then it's easily possible. We measure that single speaker, but ideally we want to apply this model to every speaker that we produce, or to every product that we produce that uses such a speaker. So it's imperative that the unit variation of the loudspeaker itself is as small as possible, meaning that every loudspeaker that is produced must perform as exactly or as precisely as possible to the specified value, because otherwise, if it doesn't perform the same way, if the nonlinearities don't look exactly like the specification, then with a generic model that compensates for those nonlinearities, we would actually introduce more distortion. So it's very intuitive. If the loudspeaker doesn't have the nonlinearities that the model is attempting to compensate for, then we would just introduce more nonlinearities. So, and this is the reason why this is now becoming possible, because active linearization is not new at all. This has been researched by many companies over the past decades. It is only starting to become possible by using loudspeakers that are as precise in production, meaning as repeatable in production as MEMS speakers are. With conventional loudspeakers, you achieve usually plus minus 3 decibel from specification. Some loudspeakers have even more variation than that, especially at frequencies above 1 kilohertz. But with USound MEMS speakers, we can achieve production tolerances of 1.3 decibel. So every produced speaker will deviate no more than 1.3 decibel from the specified value. And this is what you can see here in the graph. This is actually a measurement of all the units that were produced in 2021 of a specific speaker, of the Ganymed Achelos speaker. And you can see that even at an extremely high standard deviation of 3 sigma, which contains 99.7% of all produced units, we're still within that 1.3 decibel or plus minus 1.3 decibel deviation from the specified value, which is, if you've ever tested more than one specimen of the same model, is something that is outstanding and cannot typically be matched by conventional speakers. The reason for that being that, of course, we use semiconductor technology to manufacture the MEMS motor, and semiconductor technology, as you know, is very precise, much more precise than fine mechanics, as gluing diaphragms, winding coils and attaching them to diaphragms. Those are all process steps that introduce some deviation or some variation, but this is of course not an issue with MEMS-based speakers. So plus minus 1.3 decibel, we think is quite a competitive value. Yeah, this is what enables us to use active linearization with a generic model that is trained just on the model of the speaker, but doesn't have to be trained on the specific specimen of the speaker. So the components of the active linearization algorithm are 3 main components that are responsible for reducing the distortion, or for compensating for the nonlinearity, followed by a resampling component. The first and main block, or the main component of the active linearization algorithm, is the predistortion block. This component corrects for the static nonlinearity by applying the nonlinear transfer function. This is the same graph that we saw before. So we characterize the nonlinearity of the speaker, we characterize the characteristic curve, and by applying a transfer function that is essentially the inverse of that characteristic curve, we can compensate for those static nonlinearities. This is very easily implemented using a simple lookup table. This requires a little bit of storage, but very little processing power. So this is very easy to implement. On the bottom right, you can see how this affects the distortion of a speaker. This is a speaker driven at its absolute maximum. So you see it, we drove it consciously to very high distortion levels. And even then, even at those very high distortion levels, we already achieve a reduction from like 8% THD at low frequencies down to 3% THD at low frequencies. Now this is at or slightly outside of spec for the speaker, the input voltage. So this is more distortion than we would expect if we drive it inside of specs, but it still shows how powerful this predistortion block alone is. Now, If we look into it in more detail, there's a slight issue, because we see that the distortion does not go down to 0 just using the predistortion block. In fact, when we look at the actual waveform, the right here you see a graph of a 200 Hertz sine wave measured in coupler conditions, where the blue curve represents the raw behavior of the speaker, the green curve represents the ideal sine wave, and the yellow curve is the performance of the speaker with the predistortion block applied. You can see that it's a much better match for the ideal sine curve, but it's not a perfect match. Even though we compensated for all of the static nonlinearities, we see there is still some deviation. And this has to do with two things that we will be compensating for with the next two blocks. The first thing we need to take into account is that at high frequencies, the static model is not fully valid. So at frequencies above the loudspeaker's resonance frequency, the static nonlinearity is not completely valid anymore. So first we need to add a prefilter to the predistortion that reduces, so it's basically a weighting filter that reduces the influence of the predistortion at frequencies above the resonance frequency. So we apply the prefilter before the predistortion and then apply the inverse prefilter after the predistortion, so that the spectral content of the signal is unchanged, or the spectral content of the signal coming out of the speaker is unchanged, and the predistortion block still reduces the distortion below the resonance frequency. So the prefilter is implemented using two complementary filters, typically implemented as simple biquad filter stages, one before and one after the predistortion block. On the graph to the right, we can see how this affects the distortion levels. So with the predistortion levels, with the predistortion component, we can actually see how the distortion increases at frequencies above the resonance frequency. This particular speaker has a resonance frequency at roughly 2 kilohertz. So if we would not compensate for the change of validity of the static nonlinearity model, then we would actually increase the distortion at high frequencies. So in order to avoid that, we need to apply the prefilter. And with the prefilter, we can achieve an increased reduction of distortion around, or broadly around, the resonance frequency of the loudspeaker. Now, the distortion is already at a level that is useful for headphones, but we can reduce it even further by compensating for what is called hysteresis. So before, when I talked about the nonlinearity or about the characteristic curve, I was actually lying a bit, because the characteristic curve is not, when you look at it in more detail, is not actually easy to describe as a simple static transfer function. It actually has a different path depending on whether the input voltage is ascending or descending. So the ascending path will look, so if you apply voltage to the speaker will excurse. And if you then apply negative voltage to the speaker will excurse in the negative direction. And the path that it takes on the ascending direction is not an exact mirror image of the path that it takes for a descending direction, because of a hysteresis effect inside the motor unit. And this is a little bit tricky to compensate for, but with work from Bayana et al., we have developed, or we adapted an analytical model to compensate for hysteretic behavior that can also reduce the distortion for these loudspeakers. So with this final step, we can see it on the bottom right. With this final step, we can achieve an additional decrease in distortion. Now, pay attention to the y-axis. This is on a logarithmic level, so the amount of distortion reduction is not as significant as with just the predistortion filter, but in terms of logarithmic values, it achieves roughly the same distortion reduction. So the distortion products are reduced by the same amount of decibel, but not the same amount of percent. So with the hysteresis model, we can achieve a reduction of distortion to levels below 0.5% THD. This is actually a measurement done inside an application. So as you see, compared to the graphs that you saw before, where we had distortion values of 10% and higher, this is a measurement done in application, driven at signal levels that are more common in an actual application. So not 120 decibel, but more closer to 110. And you can see that the loudspeaker in its raw performance has a distortion of roughly 2% at low frequencies. And with the three components, so with the predistortion, the prefilter, and the hysteresis model applied, this distortion is reduced down to as low as 0.3% or below 0.5% at low frequencies. Now, the reason why I'm only mentioning low frequencies here is because this is where typical music or speech content will have the highest amount of energy, and this is typically where the distortion levels are the most problematic. Now, of course, by compensating, so by changing the transfer function of the speaker, of course, at some point we need to apply a higher voltage to the speaker, which reduces its maximum output capability. But since we're talking about influences of the amount of energy that we're reducing here is in total a reduction of SPL of below 0.5 decibel. So while there is in theory a small reduction of maximum SPL output, because we need that extra headroom to compensate for the nonlinearity, in the final product or in the final application, it amounts to a change of maximum SPL by less than 0.5% or less than 0.5 decibel. So this is absolutely not something that we need to worry about. Now, the fourth part of the active linearization algorithm is the resampling. The reason why we need to do this is because the predistortion, of course, it changes the transfer function of the signal. So it will add additional frequency components. It's a nonlinearity. It's a nonlinearity introduced to compensate for other nonlinearities. So of course, changing the transfer function will introduce additional frequency components. If this additional energy falls into frequency ranges above the Nyquist frequency, so above half the sample rate, then they would get mirrored down into the audible range via aliasing. So we recommend that for standard audio signals, which contains energy at basically 20 hertz to 20 kilohertz, we recommend to use a sample rate of at or higher than 96 kilohertz within the compensation block in order to avoid the aliasing effects. So that's why we also add a resampling block before the compensation, so before the active linearization algorithm, to avoid those mirroring effects. Now, as I said before, the active linearization, in order for it to work, we need to carefully characterize the exact speaker, meaning that all the coefficients for the lookup table, for the hysteretic model, and also for the prefilter, all of those coefficients need to be calculated specifically for each loudspeaker model. But because MEMS loudspeakers are so precise in manufacturing and they have such low unit variation, we don't need to train, or we don't need to perform training measurements for every specimen. So not for every speaker that we produce, but only for every model that we produce. So for example, USound, we have currently produced 4 different loudspeaker models. So we need to calculate 4 sets of coefficients, 1 for every loudspeaker model, but we don't need to train it specifically for every specimen. Now, the way that those training measurements are done is quite simple. So we play a test signal, which is a simple sine wave at full amplitude over the loudspeaker. So it's important to achieve the maximum excursion that the loudspeaker is capable of, so that we can train for all of its nonlinearities, even at very high levels. Then we record the acoustic response of the loudspeaker, typically by just placing the loudspeaker inside the coupler. And then using an in-house developed tool, we calculate those coefficients, comparing the test signal and the acoustic response. Now, for best performance, ideally, those coefficients should be determined by performing those training measurements inside the final application, meaning by measuring the actual earphone containing those MEMS loudspeakers. This would achieve the highest amount of reduction, which is what we can show here in those graphs. But it is generally possible to provide just a set of components or set of coefficients for the loudspeaker model and not train it on the actual earphone. Now, again, for the best performance, we should perform training measurements of the final earphone. It doesn't need to be the mass product, but a prototype earphone where the acoustic design is finished, and perform the training measurements on this. But we can achieve very similar performance with roughly 0.5% difference in performance, or percentage point of difference in performance, by providing just generic coefficients that depend on the loudspeaker model, not on the final application. And once again, training on every specimen itself is not necessary because the unit variation is low enough. So it's not necessary to measure every single speaker. It's typically sufficient to measure just an average of, let's say, 5 units. And it also provides sufficient results from measurement as just 1 unit, provided the unit variation is low enough, which for MEMS loudspeakers it is. Now, how do you actually apply the active linearization algorithm in your final product? So the ALA will run on any digital signal processor or general purpose processor, as long as it has a floating point unit. Fixed point operation is something that is generally possible, of course, but it's not something that we have implemented yet, mainly because we found that the DSPs or TVPs that will be used in those applications that we target, namely TWS earphones, typically have a floating point unit. So if your specific product only has a fixed point unit, give us a call and we'll figure something out, but we're confident that floating point operation will work. Now the ALA, of course, runs in real time. It requires memory of less than 1 kilobyte. Ideally, the sample rate would be at or higher than 96 kilohertz. 48 kilohertz sample rate is possible if we include the resampling, of course. Now, the way that we provide this is we provide a set of C functions to integrate into your final product. And we also provide the ALA coefficients that we calculate from acoustic measurements of the final product, ideally of the final product or a prototype earphone with finished acoustic design. And of course, you ask next, how can you test this before you apply for a license for the ALA? You can test this linearization algorithm by using our standard evaluation board, the Helike UAE 3010. At any firmware starting at 3.3.0 and up, the ALA is available, and the loudspeaker dependent coefficients are loaded via a JSON file. Now those will be generic coefficients, so coefficients for a specific loudspeaker model. They will not be optimized for your final application. If you send us your prototype, then we can, or if you send us measurements of the prototype, then we can calculate coefficients specifically for your prototype, but for general evaluation, those generic coefficients will do fine. To get started, you reach out to your local SELTECH contact, who will provide you with the Helike board. Alternatively, you can contact us directly if SELTECH doesn't have a representative where you live, or you can also just order the Helike board on DigiKey and get started using that. It comes with a full manual, so everything is explained in there. Yeah, this just shows the evaluation board, the development board that we have, which we use, among other things, to showcase the active linearization algorithms. It connects via USB or via Raspberry Pi platform. It can also work as a standalone unit. It has amplifiers built in to drive both dynamic speakers and so electrodynamic speakers and MEMS loudspeakers. And most importantly, it has the STM32 digital signal processor that can be used to apply the ALA to the loudspeaker using the updated firmware.